All right, just wanted to go through a quick review of the experimental side of friction that we had dealt with very early in the year. So if you look on your equation sheet, you have this equation for the force of static friction, and I can't remember if the absolute value is around the normal force, but that doesn't matter. But we had this inequality here, and that really mostly applied to this idea of static friction was less than or equal to mu times the normal force, absolute value. And this is where we always kind of look for that special permission statement in order to use the equal sign at its maximum value, because Fs at its max was just going to be equal to mu times the normal force. So static friction was always a little trickier to work with. The other type of friction that we dealt with throughout the year, of course, was kinetic friction. That one's a little more simple. That's one's associated with things that are sliding, and that was always equal to mu times the normal force. And we talked about that in connection to when we got into rolling without slipping and rolling with slipping and what kinds of frictional forces. And we'll talk a little bit about rolling towards the end of this little video. But I wanted to remind everybody about experimentally how we went about determining this coefficient of friction and how experimentally we were able to measure friction. There is no friction meter that we had in the lab. We actually took advantage of setting things up at a certain situation. So I just wanted to kind of clarify again between static and kinetic friction, and I'm looking around my house looking for things to kind of do a demonstration, and look what I found. These are, ladies are probably, when you get your pedicure, they use these to separate your toes. But it's a kind of a good thing to model what does a surface. So even a smooth surface like this, like a whiteboard, has surface irregularities. If you look at it, under a very strong microscope. So if you have two surfaces that are being pressed together, the greater that normal force, the more the things are being pressed together, the greater that value of friction, the more force it would take to kind of break these kind of bonds that are holding these things and keeping them from sliding. So if we think about static friction, these two surfaces are pressed together. You can see like the little bumps are kind of caught on each other. It's actually kind of electrostatic forces, but we won't get into that now. So it keeps pulling until it finally breaks those bonds, and then as it kind of slides along, maybe it just kind of rests on the top of it. So hopefully that gives you a sense of why static friction has this range of possible values and why its peak value is a little bit higher. But let's talk about what it looks like experimentally. So one of the first experiments that we had done, if we're going to use a force sensor to measure static friction, we had some kind of block here, and then we string, and then we were pulling it with some kind of force sensor here that was connected to our LagerPro. So what made this the situation, how we had to set it up, we needed to be very careful about that so that we could take advantage of, because this force sensor is really just measuring some kind of tension force. And here is where our friction force is. So if we set our experiment up correctly, then we could say that these two are equal to each other. And the two conditions for that to be true is it needs to be pulled horizontally on a horizontal surface, and we needed to be pulling it with a constant speed. Because if we look at our free body diagram, so let's say we have our normal force acting upward, we'd have a weight vector acting downward. Again, if we're on our horizontal surface, then these two forces would be equal to each other. So then if we knew the weight of the object, we could know this normal force right here. And again, if we did it on a ramp too, we just have some cosine or sine terms in there. It's not a big deal. And then if we pull it with a constant speed, then this frictional force here is going to be equal to the force sensor reading here. And then we could, as long as we were doing this in our lab, then what we saw on LagerPro on our output would give us the reading of what the force was going to be. And now let's just do a quick review of what the sensor reading looked like. Again, I'll erase this. Not the best eraser. All right, there we go. So the graph of a force sensor. So the sensor reading is going to be as a function of time, and then you had your force sensor reading, and then if we started at rest and begin to pull it, it would have a range of possible values for that static friction until it starts to move. It reached this peak value, and then it kind of leveled off and a little bit bumpy there. So if this is what the graph would look like for our force sensor, all of these values are going to tell you the range of possible values of static friction. This peak value right here was our max value of static friction, and then all these values over here were telling us the value of the kinetic friction. So in the lab, when we wanted to determine what mu was, we wanted to create a graph from which the slope of that line would be our coefficient of friction. So if we had a graph and I graphed friction versus the normal force, I'm going to get a linear graph where the slope is going to be equal to mu. So all we needed to do is get a variety of normal forces. And how did we do that? We varied the mass of the object, and then we measured the value of the frictional force from our graph. So we could either measure Fs max here and get a graph of that, or we could measure this value of Fk here. And for each of these graphs, we could determine what the coefficient of sliding friction was, mu sub s, or we could determine the coefficient of sliding friction, mu sub k, and static friction, which was mu sub s, not sliding. So this is kind of how we set it up for objects that were on a horizontal surface. So, but what would we have to do if we didn't have a force sensor? How could we measure mu? Well, we could still do it. Some other ways that we could possibly do this, if we had access to a pulley, we could put our block on the pulley here, over a pulley, and then put some other mass right here, and we could increase this mass until it just starts to slip, or is moving at a constant speed. And then we could do the same thing as long as we had, instead of using a force sensor reading, we'd have to do a little bit more dealing with the weight of this object. But as long as it was just starting to slip or moving at a constant speed, then the weight of this would be equal to that tension force, and that would be equal there. So that would be one way that you could do it, a little bit more elaborate. Let's see, what else if we didn't have a force sensor? If we remember, we could use just a ramp. So if we took our block and put it on a ramp here, and we had a protractor that we could measure this angle, let's go through the force diagram for this block. So let's say we have a normal force acting perpendicular. We have our weight vector acting downward, and then we're going to have our static friction, or let's just say our frictional force. So it's either constant velocity or another. I'll get another color here. And then we're going to have our components of our weight vector here. And this is our angle theta in there. So if this is in equilibrium, then we know that the frictional force is going to be equal to mg times sine theta. And we also know that friction, we're talking about Fs max or we're talking about kinetic friction, either one of those is going to be equal to mu times the normal force. Let me get back over here. And that's going to be equal to mu times mg cosine theta. So if we set these two equal to each other, we get mg sine theta is equal to mu mg cosine theta. And this hopefully is a familiar result because we've done this before. We get that mu is equal to g sine theta over cosine theta. And of course, this whole thing right here is just tan theta is equal to mu. So if we have a protractor and a ramp, we could do this experiment to measure the value of mu. And we did this as kind of a wraparound activity, just tilting the ramp until it just starts to slip, and that would give us Fs max. Or if we had some means of making sure that it was moving with a constant velocity, that it was sliding down the ramp with constant velocity. So that's another way we could determine mu, and we wouldn't need a force sensor at all. You would just need a ramp. All right, one more thing I just wanted a quick review, and this is good for rolling motion. That force of static friction, which is acting as our torque to cause something to roll down a hill. If we remember, it's static friction because it's not sliding. Again, we're talking about rolling without slipping. This is just a quick review. If our object here is going down this way and our angular velocity is increasing, then static friction is providing that torque to increase the angular velocity. And then one of the trickier things that we dealt with in class is, what if our object was moving this way and our angular velocity was beginning to slow down? Which way would static friction be acting? Again, static friction needs to provide that torque around the center of mass to cause it to stop to start to slow down. So if it's rolling up the hill that way, static friction needs to provide that torque still up the ramp so that it provides that counterclockwise torque to cause this angular velocity to begin to slow down. So that was just a kind of a quick review of rotational static friction. I thought I'd just kind of throw that in there just as an aside.